The next topic in this section is electricity, and in this section we will talk about charges and how they interact with each other. To truly understand electricity, first we have to start small. The basic building block of all matter is atom, and this atom is composed of three subatomic particles, namely protons, electrons, and neutrons. At the very center of the atom, if we see here in the image, uh, is the nucleus, and this nucleus contains protons, and which have a positive charge, uh, which has which has a positive charge, and nucleus also contains neutrons, which are neutral, meaning they do not have any charges, and orbiting this nucleus are the electrons. We can see in the image here, these are electrons. Electrons are arranged in distinct cells and carry a negative charge. Protons carry a positive charge and electron carries a negative charge, and these electrons rotate about orbit this nucleus at different cells, and the arrangement of these subatomic particles is what gives every element its unique properties. So based on this nuclear proton, neutrons, and electrons, every element has its unique properties. In its natural state, an atom is electrically neutral. This is because it has an equal number of protons and electrons. We can see in the first diagram here, if there are two protons and two electrons, the the net charge in the atom will be 0. That also means that one proton and one electron has the same amount of charge, but proton is positive charge and neutron is negative charge. Sorry, electron is negative charge. And but atoms aren't always stable. So naturally, in its if the protons and electrons are in same numbers, the atom will be electrically neutral with a zero net charge. And atoms aren't always stable. They can either gain or lose electrons. When an atom loses an electron, it has more protons. We can see in this image, it had two electrons, and it lost one of the electrons. Now there are two positive charges but only one negative charge, and if we calculate the net charge, we have plus one negative charge. We call this a positive ion. So if this atom loses or gain any electrons, it will become non-zero net charge, and we call this non-negative non-zero net charge atom with non-zero net charge as ion. And if it loses an electron and become positive net charge, we call it positive ion. And the other way, if it gains gains electrons, and then if we calculate the net charge, we have three negative charges but only two positive charges, resulting in negative net charge, and we call it a negative ion. The standard unit for measuring electric charge is coulomb, and the symbol for coulomb is a capital C. And the transfer of this electron is the very basis of electricity. And whenever we are saying electricity, current is flowing or something like that. Basically what we are saying is what we are observing is the flow of electrons from one point to other point. And the unit of charge is coulomb, and we can see the charge in an electron is very small, and the numerical value of charge of an electron is minus 1.602 times 10 to the minus 19 coulomb. So the first fundamental rule of electrostatics is a law of charges. When we say electrostatics, we are talking about charges in a stationary or static form, meaning charges are stationary and they are continuous, not uh, flowing continuously, and charged particles follow this law of charges, and the law of charges states that uh, the law of charges states that like charges repel each other and unlike charges attract each other. And we can also see in the figure here we have a positively charged rod and negatively charged silk rod. And if we see here when we bring this cloth close to the positively charged rod, it's rotating toward the cloth. And if we see in the second image here, there is a positively charged rod, and when we bring this positively charged rod close to this other positively charged rod, it is repelling it and causing a rotation in other direction. And we can similarly see here, if we bring two negatively charged silk cloth together, they will repel each other. And we can also do this if you have a glass rod and a silk cloth. You can do experiment. If you rub the glass rod with silk, then electron will transform from one object to other object, making one object positively charged, one object negatively charged. And you can repeat this whole experiment to understand how the charge works. As we said, the study of stationary or static charge is called electrostatics. There are three primary methods by which we can transfer or create these static charges on an object. The three primary methods are friction, conduction, and induction. Friction, rubbing two different materials together, can cause electrons to transfer from one material to other materials. And we can think an example of rubbing a balloon on your hair. The balloon becomes negatively charged, and your hair becomes positively charged, causing them to attract toward each other. And we also saw in the previous example the glass rod becomes positively charged when rubbed with silk, and the silk cloth becomes negatively charged. In conduction, this is a direct transfer of charge. When a charged object physically touches a neutral object, for example, if we have a neutral object here and a charged object, and if they touch each other, it will transfer the charge from one object to other object, and this method is called conduction. When a charged object physically touches a neutral object, electrons will flow between them until they share the same charge. So both of the object will have a positive charge. and then we have induction. This is an interesting method, and it allows us to charge an object without ever touching it with a charge source. So we do not need to touch the charge source in order to uh, charge an object by the method of induction. We can look at more on the charging by induction method. We can see here in the first figure, we will start with two neutral object. We have two neutral spheres here in contact with each other. They are contacting each other, but they are isolated from the ground. They are not grounded to the ground, and they have an equal number of positive and negative charge, meaning initially they are neutral with equal number of positive and negative charges, and then we will bring a positively charged rod near one of the sphere. We bring a positively charged rod close to the first sphere, but we do not touch it. So we will just bring it close, and we will not touch it. What it does is the positive rod will attract the negative charges from the sphere. We can see the negative charges are moving to close to the positively charged rod, because we know that opposite charges attract each other. So the rod is positively charged, and all the negative charges from this sphere are attracted toward the positive charge, and this positive charge of the rod attracts negative charges from the sphere, and these negative charges are collected at this end, and once these negative charges are collected here, it makes the sphere, it lifts the other part of the sphere with a positive charge, more positive charges, because all the negative charges are at this end. And if we separate this object now, since these charges are isolated here, if we separate these two objects, two spheres, we can see this is negatively charged, and this is positively charged. And if we again bring them together, because of the positive and negative charge, they will attract each other. So basically, without even touching this neutral sphere, we are able to create these static charges on spheres, one positively charged and one negatively charged, even after removing the charged rod. We talked about the attraction and repulsion between charges, and since there is an attraction or repulsion, that means there is a electrostatic force between charges. There is some force between these charges that will either attract, the force is either attractive or repulsive based on the polarity of these charges. We can see in the first image, if there is a negative and negative charges, the force is repulsive, and if one of the charges is positive, one is negative, and the force is attractive. And the magnitude of this force between two charged particles is described by Coulomb's law. The magnitude of this force, electrostatic force, is defined by Coulomb's law, and the formula is the Coulomb's law. The formula given by Coulomb's law is force is equals to K times Q1 Q2 over R square. Here K is the proportionality constant, and the magnitude of this proportionality constant is 9 times 10 to the 9 Newton meter square per Coulomb square. And Q1 Q2 are the charges, and R is the distance between these two charges. And this law tells us two important things. First, we can see from here that the force is proportional to the product of the charges. Proportional to the product of the charges, and that means more charge means a stronger force, meaning if the amount of charge is, if the charge is bigger, then the force will be bigger as well. And secondly, it also tells us that the force between two charge particles is inversely proportional to the square of the distance between them. So if this is the distance, then the force is inversely proportional to 1 over R square. And what this means is that if you double the distance, if you change the distance from R to 2R, then the force becomes 4 times weaker, because it will be 1 over 2R square, which is 1 over 4R square. So doubling the distance between the charges will make the forces 4 times weaker. And we should also note that the Newton's third law also holds true in the case of charges as well. If there is a force on F from charge Q1 toward Q2, then there will be force from charge Q2 toward Q1, and these forces here in the image, force F12 should equal to force 21, but in an opposite direction. So this force is going towards right and this force is going toward left. They are equal and opposite, and that means Newton's third law holds true for the Coulomb's law as well. Now let's look at an example. Here we have two positive charges. We have two positive charges, one 2 microcoulomb and other of 7 microcoulomb, and these charges are separated by a distance of 20 centimeter. We want to find the force they exert on each other. So the question is asking, what is the magnitude of this electrostatic force that each charge exerts upon the other? And the first, we need to convert our units to be consistent. Before doing that, we said we talked about the unit of charge, right? And we said the SI unit is coulomb, and the given problem is in a microcoulomb. So let's change this charge. The first charge is 2 microcoulomb, and micro is 10 to the minus 6 coulomb. And then the second charge given is Q2, and then we need to Q2 is 7 microcoulomb, and we need to convert it into coulomb as well. And the distance is given in centimeter, and we need to convert it into meter. And in order to convert it, 20, we know 100 centimeter is 1 meter. So this is 0.2 meter, and from the Coulomb's law, the electrostatic force between two charged particles is given by proportionality constant Q1 Q2 over distance square. Proportionality constant is 9 times 10 to the 9 Newton meter square per Coulomb square, and then Q1 is 2 into 10 to the minus 6 coulomb times Q2 is 7 into 10 to the minus 6 coulomb over distance is 0.2 meter squared, and this is 2 times 9 times 2 is 18, 18 times 6 is 126, 126 times, we can see here there are 9, 10 to the power 9, 10 to the power minus 6, 10 to the power minus 6, so 9 positive power and 12 negative power, so this results in minus 12 plus 9, 10 to the power minus 12 plus 9, and the unit, this is coulomb square, coulombs will cancel out, and we can also see here there is a meter square, so meter square and meter square will cancel out, so this is Newton over 0.2 squared. And if we calculate this, if you use a calculator and solve this, 126 into 10 to the minus 3 Newton over 0.04, and if you solve this, you will get 3.15 Newton. So the force between these two charges, 2 microcoulomb, two charges with a magnitude of 2 microcoulomb and 7 microcoulomb charges separated by a distance of 20 centimeter has a force of 3.15 Newton. And we can see one more example. Here we have a third charge Q naught placed between two charges Q1 and Q2. Both Q1 and Q2 exert a force on Q0. If we look at here, all these charges are positively charged, and we know that like charges repel each other, meaning this charge will repel this charge, and this charge will also repel this charge. And what the question is asking is that 2 point charges Q1, Q2 are separated by a distance of 30 centimeter. So the total distance is 30 centimeter between Q1 and Q2. A third charge Q0 of 4 microcoulomb is placed between them as shown. So the third charge is here, Q0 is placed at 10 centimeter from Q1 and 20 centimeter from Q2. The force exerted by Q1 on Q0 is 10.8 Newton. So the force from charge 1 on charge 2 is 10.8 Newton. We can write it as shown in the figure. This is F1, so F1 is 10.8 Newton, and then it also says the force exerted by Q2 on Q0 is F2 is equals to 1.8 Newton. What is the net electrostatic force acting on Q0? So we can see, since this is a force, it's a vector quantity. So we will apply a vector addition. So F net is equals to F1 plus F2, and if we use our usual sign convention and say that going this direction is positive and this direction is negative, then we will have 10.8 Newton minus 1.8 Newton is equals to 9 Newton, and we can say since the larger number it was going from left to right, the resultant will also orient from left to right. So the net force will be in this direction with the tail from in the left and the arrow in the right. Or we can just say 9 Newton to the right. Now let's talk about electric field. The concept of electrostatic force, we talked about electrostatic force, and we said if we have a charged particle, it will exert some force on other charged particle. So this concept of electrostatic force leads us to the idea of electric field. And an electric field is a region around a charged particle where it can exert a force on other charge. For example, we can see here in the first figure we have a positive charge, and if we were to put a test charge somewhere here, it will exert some force on this charge. So the electric field is basically the region where this force will exert some forces if we were to put some charge in that region. We generally visualize this electric field using this vector notation, vector notation representing the electric force. And if we look at these figures, we can see from the positive charge, generally the electric field is outward, and in the negative charge is flowing inward toward the negative charge. Basically the direction of this electric field is defined by defined by the force experienced by a test charge, and generally the test charge we will use is a positive test charge. For example, if we have a test charge here in this field, so let's start from the 0. Say we have a positive charge here, and we also put a test positive charge. This is test, and we know they repel each other, meaning the force, the electric field should go from the source charge, and it should be outward. And instead of a positive instead of a positive charge, what if we have a source that is a negative charge, and we put a test charge in the region of electric field? Then what will happen? This is a negative charge, this is positive charge, so this negative charge will attract this positive charge toward it, resulting in this kind of electric field. So the direction of electric field is basically for a positive charge, the field lines point radially outward, showing the direction of a positive test charge would be pushed away from the source charge, and for a negative charge the field lines point radially inward, showing that a test positive charge will be attracted toward it. So basically this is defined by a positive test charge. And we should also see that since this is a vector notation, if you look at this vector, these arrows, we can see the inner arrows are bigger, and as it gets outside, as it go away from the source charge, is getting smaller and smaller. That's the same for all this vector notation. It's very long in the close proximity from the source charge and gets smaller as it moves away. And what does that mean? Since it's a vector notation, that means the electric field is stronger close to the electric charge, and it gets smaller as it goes further from the uh, charge source. And generally whenever we need to show this electric field, this is how we generally show the electric field. We can see here we have negative charge, positive charge, and like we just explained in the previous slide, this electric field is going from positive charge to negative charge like this, and there's a whole bunch of field, and it's all going from positive charge to negative charge. These other lines where we see like this, these are also going from positive to negative, but with a very big circle like this. So all these forces, this will be at some infinity. This electric field always passes from positive to negative charge, and we can draw it like this. And also remember whenever we have a point charge particle, the electric field will be radially in all direction surrounding the charge particle. And the strength of an electric field, like we talked before, the strength of an electric field is not uniform. It is strongest close to the charge and gets weaker as you move away from the charge. We can define the electric field as the force. We can define here the electric field is defined as the force per unit charge, and the charge we use is a test charge, and generally the test charge we use is a positive test charge. And mathematically we can write electric field is equals to force experienced by this test charge over the charge of the test charge we are using. And this equation gives us a way to quantify the influence of a charge at any given space. For example, if we were to look somewhere in this point or somewhere in this point, this equation will give us a way to quantify this force. And we should also note that we already said this electric field is stronger when it's close to the charge and gets weaker as it gets away from this charge, meaning the electric field is a function of the distance from the source. And we generally write it like this in this way, saying this electric field depends on the distance. And we can rearrange the previous equation where we said electric field is force over charge, and we can also rewrite the force experienced by a test charge in an electric field. And the force F on a charge q, the force F on a charge q in an electric field E as a function of R is given by F is equals to QE, and F is equals to QE, where E is a function of distance. We can see here This is a source at the center, and the electric field is going outward, radially outward here, and then we have a test charge placed somewhere here at a distance r from the source charge, and the force experienced by this source charge is given by whatever the charge is of this test charge times electric field. And now we will talk about electric potential. Electric potential is defined as the work done per unit charge to move a test charge from one point to another within an electric field. So this is similar to what we did in when we defined a potential energy against gravity. So how did we define potential energy? We had ground here, and we said whenever we are moving this object against gravity, we will transfer some of the energy in the form of potential energy, and that potential energy was given by the weight times height. The similar way we can also define electric potential using electric potential energy, where if we look at the electric field here in the figure, let's look at the figure. We have a positive charge here on the top denoted by this plus, and then we have a negative charge in here denoted by minus, and they are parallel to each other. If they are parallel to each other, the electric field are just straight lines passing from going from positive to negative. And the potential energy, and we have a positive test charge here at a distance at some arbitrary point. We have a positive test charge, and if we look at this electric field, it's going from this part toward the negative charge, right? And if we were to put a positive test charge somewhere in this electric field, naturally this positive charge will repel this positive charge, and this negative charge will attract this positive charge. So this positive charge will move toward this negative charge naturally, similar to what the gravity will do. If we were to drop this object, the gravity will naturally pull this object to the ground, and it will lose potential energy, right? That will be the same case here. We have a electric field, and we have a positive test charge. If we naturally leave it, it will move toward the negative charge, losing some amount of potential energy. And if we were to, instead of leaving it naturally, if we were to pull this charge toward the positive charge, we have to do some extra work, or meaning we have to apply some external force similar to moving this object against gravity. Then we have to do some amount of we have to apply some amount of force in order to move this positive charge against the electric field. And if we move if the force applied is F, and the distance covered by this positive test charge is D, then basically we can calculate the work done, and using the work done we can calculate potential energy. As we know, work done is basically the change in energy. And like we did in gravitational field, we can define change in potential energy as charge times electric field times distance covered. So charge times electric field is the force and d is the distance covered from here to here when we apply this external force to move this positive charge from its original position by a distance d. And the unit of electric potential is a volt and it's an scalar quantity. And